So our next topic that we're going to talk about is, we call it photons and biophotons. Now, photons are packages of lights, and lights can be in a wave form, or it can be as a particle. We had to do this at A-level physics, I remember, some years ago now. Was light a package of, did it have a particle, or did it have a wave? And sometimes it would react in one way, and sometimes it would react in the other. And we now know in quantum physics that it's both, and that both are actually the same thing. And a lot of it depends on whether somebody's measuring something as a measuring device. If it's being measured, it's usually as a particle, and if it's not measured, it's a wave, or a wave of possibilities, which makes life very interesting. So light isn't a substance, but it is a movement of electrons when it's measured. Okay? So those are photons, or packages of light, as they call them. And they come ultimately from the sun. So all our light in our universe, or our solar system, ultimately comes from the sun. If the sun went out, we wouldn't survive very long. Okay? So what happens is that light is converted into chemical energy in the leaves through chlorophyll. And the chlorophyll is a green compound in the leaf which converts sunlight, water and carbon dioxide, to make glucose. And that's ultimately the food to feed the plant, and then feeds the animal that lives on the leaf, and so on, and we eat the animal, or we eat the leaf, and so we're at the end of the chain of the food. What's interesting is that the leaf actually does not absorb green. It absorbs red and it absorbs blue light, and it reflects green. The green, although people eat your greens and everything else, greens are good for you, actually it's not the green that is. The leaf says, I don't want the green, get rid of the green, I'll reflect that to anybody who's looking at it to make you imagine that it's green. It's a myth, because if you turn the light out, the sun out, everything's black. It doesn't have any light. It's only a reflecting device, the leaf, that is absorbing red and blue and reflecting green. And you say, it's green. Okay? You see that? So it's interesting, if you teach people that concept, yes. So we know that chlorophyll actually picks up and absorbs red and blue. And it's those ends of the wavelengths which actually convert water and carbon dioxide into sugar. Now, some 25 years or so ago now, I did my first seminar on toxicity in Bath. And I liked in those days to take a new topic, and the problem, or the concept of toxicity, was a new concept. And I don't really know very much about it, apart from the fact that Joe Schaefer and myself have been to Russia, and we knew we were toxic when we got back because the pollution was, very heavy. So I got interested in the problems of detoxification, but mainly because I was irradiated. We had a lot of radiation poisoning from there. And I got hold of Jeff Bland at that particular time because he was involved with looking at making products through HealthCom to detoxify. And so I started listening more intently to his researches, and he was promoting these things called liver phase 1 and phase 2 detoxifications, and banded these words around like cytochrome P450, sulfation, glucuronidation, and Jeff says it at 10 times the speed that I do. And I thought, well, what is this cytochrome P450? So I looked it up in Harper's Biochemistry, and it said there that that these enzymes emit 450 wavelengths on a chromatography plate when they're exposed to carbon monoxide. So I put that away then for 24, 25 years. I think, sweat. And it never dawned on me until I sort of got interested in this again from reading Fritz Popp's work more recently, last year, I think. That I thought, 450 is in the blue range. Because by that time I started printing out what is all the wavelengths and things. And I thought, that's in the blue range. Let's reread that again. So cytochrome P450 as a family emits a blue light on a chromatography plate there when it's exposed to carbon monoxide. It's interesting, because I can make on the computer 450 nanometers, which is what the measurement was, and see what happens. So what I did is I make it up as an acetate, and then I found that we did a vial of carbon monoxide, and I found when people weakened to carbon monoxide, they weakened to the 450 nanometers. So it was an exact ability to actually tell whether the person has got carbon monoxide poisoning. Well, have they been by a car exhaust or whatever? Not necessarily, because they actually produce carbon monoxide in the mitochondria at complex 4 when we're hypoxic. When we have a low level of oxygen, the heme compounds start to break down and they produce carbon monoxide as a byproduct. So we actually gas ourselves. So if a person glows with 450 nanometers, it means they're basically hypoxic. They're building up carbon monoxide instead. So cytochrome P450 was named because it was discovered that the microsomes, those are the crushed up particles of the endoplasmic reticulum, etc., in the cell, have been chemically reduced and then exposed to carbon monoxide. It exhibited a distinct peak here, as you can see, at 450 nanometers. So we measure light or color in nanometers. That's the wavelength of light. So this is carbon monoxide, 450, hence the reason it was called cytochrome P450. So it made a bit of sense. Now, at times in hypoxia, carbon monoxide, if the hypoxia is severe, not only do we produce carbon monoxide, but we can actually produce cyanide, which is a lot more toxic than carbon monoxide. So a person who's in severe problems in complex 3 and 4 in the mitochondria may produce cyanide. And cyanide, in Harper's biochemistry, emits at 430. So you could actually tell, with these two subtle differences in the wavelengths, if a person weakens to 430, they may have a high level of cyanide, in other words, they're extremely hypoxic. So let's just go back. Can you see the difference? There's a slight difference. There's lots of different colors in the blue range. So if you have a look at 450, and now I'm going to go to 430, see there's a slight tinge of red a little bit more there. It's heading towards the violet, or more towards this sort of indigo type of color range there. So when we look and we see a color, when you see a particular specific color, like a leaf on a tree, we're looking at something which is reflecting to us within a wave band. Okay? Now, what we see is only a very small fraction of the electromagnetic wave band over there. Okay? It's an infinite small because it goes infinite in that direction and infinite in that direction. Okay? You can get infinitely bigger, longer, and infinitely shorter. Okay? So what we actually see is a very, very narrow wave band. And we see between 770 nanometers here and 385 at this end. So what happens beyond 385 is we don't see. And when we go above 770, we don't see. So we can't see. It doesn't mean it doesn't exist. We can feel it. If you go down here, you may get burnt. But you get burnt by the radiation because it's a shorter wavelength. Up here, you'll probably feel the heat, the hotter you get here. But you won't see it, okay? And this is the thing that you will not see beyond 770. Now, what makes it even more interesting of what we see is at 645 nanometers here, we go from orange into red. And from 645 right up to 770, it's red. It doesn't change, okay, to the human eye. We can't tell the difference. And we can't print it on the computer. We cannot see any difference in the red. Okay? But it is different because some animals can see, and some will actually create a device which produces at 630, 640, 670, 700 nanometers. It has a different wavelength, but we can't see it. The human eye is unable to see differentiations in the red zone beyond where red starts at 645. So to us, the whole of the red zone is red. So when we give you a red acetate, it covers the whole lot because we can't see anything different. Okay? Then if you go down here, you can see orange is quite small. Yellow is very small, as we'll see. Green is big. And then there's an odd area between green and blue, which is called turquoise, which is not a primary color. Blue, and then you get this blue with a bit of red called indigo, and then violet right at the extreme end. down to 385 nanometers. Beyond that, we can't see anything. So when you see an ultraviolet bulb, in somewhere, you go to a disco? Go to a disco store? No? Oh. Okay, when you go to a disco and you see an ultraviolet bulb, you see a violet light, don't you? But you actually don't see anything. You can look at the violet light, so you can see violet, but the light that's coming out of that between there and you don't see. But if you do that, you see your teeth glisten, and any dust that you've got on you shines up, doesn't it, on the ultraviolet. That's in the early ultraviolet stage. So because the bulb looks violet, that's not the ultraviolet. You cannot see the ultraviolet coming through. All right, so you've got to remember that. So you can actually make, and we can make acetates in the near ultraviolet, which you won't see. You can see a color in the actual acetate, but the light that comes through you won't see, but the body recognizes it. Okay? Now, some people can see in the ultraviolet range. People who've had cataracts done. If you've recently had a cataract done, and you've had the cloudiness removed in your eye, and you haven't got the lens absorbing the ultraviolet goes in there, and people can see violets, which they've never seen before. Like your top there, they see beautiful violets, absolutely beautiful violets. But unfortunately, after a few months, it goes. So if you do have a cataract operation and you can see lovely colors, make the most of it, because after a couple of months, they disappear again. Now, some animals can see in the infrared. Owls and birds of prey can see in the early infrared, and that's how they can catch their prey, particularly mice. Because mice drop urine, they're not house trained in any way in the fields, so they drop urine very frequently. So the hawk or the owl at night time can spot these drops of urine because they're giving off heat in the infrared, and to go shoop, straight down, and they stand no chance at all. The owl will just fish them off again. So and we now do this as soldiers, don't they? We have infrared goggles so you can see at night time. So beyond 770 and beyond or under 385, it's invisible for us to see colors. Okay. So the original colors, which were done through Isaac Newton's spectrum experiments through a prism, he put a bright light through, as you know, and 7 colors came out. And they were the red, orange, yellow, green, blue, indigo, and violet. And when he put each of those through a second prism, they came out of the second prism at a particular angle, each one, the angle unique to each color. And that's why he said these are 7 primary colors. They were actually had their own colors. The mixture ones, like turquoise and things, didn't. Okay, so that's why he said there are 7 primary colors, because they have a specific refraction index through the second prism. Now, we, through the work of Philip Walpole and Hilary, put together some years ago the concept that the colors were associated with the meridians. So we put that the yang meridians, which begin on the end of begin and end on the face, were in the following way: stomach, triple warmer, large intestine, conception vessel, governor vessel, small intestine, and bladder. Now, you're all familiar that when people get SAD syndrome in the wintertime, they're better if they have a light box. And the brighter the light, the more they cheer up, the more they improve their serotonin. Okay? But if you put violet in front of that, it cheers them up a lot quicker. And because it puts the wavelength in of the bladder meridian, which stimulates then the serotonin. So it's 10 times more powerful, or probably more accurately, 12 times more powerful to put the color to boost the actual meridians itself that you want to. So with SAD syndrome, we know that it's associated with low levels of serotonin in the wintertime. So if you put the violet color on the light box, it boosts them up as far as their serotonin levels. So we knew that each meridian was associated with a color, and this has been known for quite some time to tune that in. What nobody's done before, and Philip and Harry came up with the idea, is that the yin meridians, which should be the opposites, if you like, were the complementary colors. So a complementary colors is everything that isn't that color that you're looking at. So let's take an example here, which is very good, is red. So if we look at the simplest of spectrums, which would give us 3 real prime colors in light, which would be red, green, and blue. Okay, that's the prime 3 ones, red, green, blue. And make a third of the circle up of each one of those. If you take red out of that, you're left with green and blue, aren't you? So green and blue together make turquoise, or cyan as it's called on the computer pad. So therefore cyan is the complementary colour to red. And we know that the complementary meridian to the stomach is the spleen. And we're meeting a lot of spleens at the moment. So we would expect, therefore, our spleen patients to weaken to this colour because it will be emphasising the problem that they've got too much, if you like, histamine in. So let's take another example. Blue and yellow. So yellow is halfway between red and green. So if you went opposite that in your circle, you would find blue. So if you take blue out of the spectrum, you are left with green and red, and halfway between that is yellow. So don't get confused with pigments, because mixing paints is different from mixing light. So in lights, you find that it's red, green and blue are the primary ones, and in pigments it's red, yellow and blue. Okay? So don't get muddled up with your paints and as opposed to your lights. So basically the yin meridians are the complementary colours to the yang meridians. So complementary means it's everything which isn't the one that you're looking at. So the whole makes white light. So if you added red and cyan together, you'd have no light at all. In other words, you would have pure light as a foam. Okay. So every one of the prime meridians here has a complement. Okay, so when we have triple warmer, which is orange, the complement is on the light blue side. So each one, it has a complementary color. So to me, you see I'm gallbladder here, so my complementary color would be yellow. So that would be, if you like, if I add yellow to me, I make the whole. So yellow would be complementary, which in fact makes a therapeutic color, as we'll see. So for me, I would be, give a yellow would, as a light, would be therapeutic for me. Okay, so do not get these confused, these colors, with the three constitutional body type colors. Those acetates which we've used for many years, the red, the green, and the blue, are to do with light from outside coming in, not from light inside coming out. So light from outside that goes through those acetates into the retina of the eye are called photons of light, and they work from outside, as we'll see. The biophotons, which is the light that comes from within us, works regardless of whether you've got the clothes over the acetate or not, as I demonstrate. So the history of biophotons was Gerswitz was one of the first pioneers in this field in the 1930s in Russia. Dinsha, who developed the work of spectroscopy, again in the 1930s, 40s, and 50s. Fritz Popp, who was the physicist in Germany, who was able to actually measure these low luminosities of light that come out of the human body. Philip Sykes, who's a chiropractor. I think he's retired now. Have you come across him, Philip Sykes? I think he's been retired. He was down in Dorset. He sent me a whole bundle of work on Fritz Popp years ago, which I tried to read. And then I resurrected it some months back or a year ago. And it was really interesting. I tried to contact Philip again, but I can't seem to get hold of him. And then Philip Walpole and Henry Pittman took Philip's work up and my work with the colours. And then more recently is Francis Crick, who was Crick or Watson, who developed the DNA. And his topic, as we'll see, he's developed this science called optogenetics, where he can turn genes on and off by simply changing the wavelength of the colour that they're exposed to. Now, Popp, who was, as I say, Fritz Popp, who was a German physicist, chose to work specifically with ultraviolet light. And because of the experiments of the Russian biologist Alexander Gerswitz, who, while working with onions, which is a strange thing to work with, but he's a biologist, working with onions in 1923, discovered that the roots could stimulate a neighboring plant's roots if the two adjacent plants were in quartz glass pots. Now, quartz is transparent, okay? So it allows certain light to go through. But not if they were in silicon glass pots, which is not transparent. Okay? The only difference being that the silicone filtered ultraviolet wavelengths of light, while the quartz did not. So Gerswitz theorized that onion roots could communicate with each other by ultraviolet light. So there was a wave band of light emitted by an onion in this case, which could stimulate the growth of another onion. And it really didn't matter the distance to some extent, as long as they were exposed to the wavelength. And this is really interesting because a lot of more modern research has actually proved this. And the simple way is, if I don't feel very good, I give Sam a call and say, come on a minute, Sam. And I'll kind of stand by Sam for a bit. And ideally, I'll touch him with two hands and I'll suck his energy out. Okay? Because I take his energy because I'm in his vicinity. All right? Have you felt the same thing in the other way when a patient comes in who's got such low energy, you think, heaven, I've got to charge myself up on the battery on the mains after this person's been in, because you think, ooh, because they've taken your energy away. Okay? So it works both ways there. So we can actually give energy to our patients, but we can also take it if we don't feel so good. They go back and feeling miserable, but we feel a lot better at the end of the day. So being in the contact, in the presence of somebody with a lot of energy gives you energy, doesn't it? And as long as they can keep their energy, they're doing all right as well. This work has been really taken into biology now much more, and is working now in very interesting fields in animal experiments as well. And then what fascinated me was that Pop discovered was that benzoapyrene, which is a particular carcinogenic compound produced in the smoke of industrial chimneys. Now, we don't see so many of these now, but when you used to have big chimney stacks, smokestacks around, the inside, the smoke, the soot inside there was highly carcinogenic. And the main carcinogenic substance was called benzoapyrene. Okay? This is the substance which is really, really very carcinogenic. When Joe Schaefer and I went to Siberia the first time in 1991, we went to this very heavily industrialized city called Novokuznetsk. And all around the city were the factories. So no matter where you went, the smoke went into the city. It didn't matter which direction it was. And from the moment you got there to the moment you left, almost, your eyes stung. And that's when you know there's something heavy in the air. And we didn't know what it was. But when we got back, we discovered that Novokuznetsk had the highest level of benzopyrene of anywhere in the whole world. And nowadays they've pulled all those old-fashioned chimney stacks and industries have all died there. But benzopyrene in the 1970s, when Pop did his work, was the major one that they studied as a carcinogenic substance. So what he discovered that benzoapyrene, the cancer-producing one, absorbed the ultraviolet light. So when he fired the ultraviolet light that Gerswitz had, it absorbed the light, then re-emitted it at a completely different frequency. Okay? It was a light scrambler. So it went out through the substance and was dispersed in different directions. Okay? And the benzoepyrene, which is harmless to humans, which is an isomer of it, which is harmless, allowed the UV light to pass through it unaltered. So it didn't change it, which was an interesting concept. And that the first one dispersed it, and the other one didn't, which was harmless. Pop was puzzled by the difference and continued to experiment with ultraviolet and other compounds. He performed his test on 37 different chemicals, some cancer-causing and some not. After a while, he was able to predict which substances could cause cancer. In every instance, the compounds that were carcinogenic took the ultraviolet light, absorbed it, and changed it or scrambled the frequency. Each of the carcinogens reacted only to light at a specific frequency or wavelength of 380 nanometers, which is just in the early ultraviolet. So it's beyond what the human can see, in most cases, in the ultraviolet. So it's the very early ultraviolet range. So what we thought, this is interesting. Could this be a way of actually diagnosing carcinogenic substances? And the answer is yes. You can diagnose a carcinogenic substance using this. But there are people, many of us, and all of us at some stage will weaken to 380, which actually doesn't mean we've got cancer. What it means is we've got something genotoxic has occurred, which has created a mutation in our DNA. And we call these polymorphisms. So don't worry if you weaken to the 380. At some stage, we all weaken to 380 because we've all inherited genotoxic reactions or mutations within our DNA from either mum or dad, or because we've been exposed to toxins. But we can use this, first of all, and we were using this during the summer, to detect carcinogenic substances. So let's, could you find, I've got to 380 here. So let's take, you're in good shape now, aren't you? So come and lie down. What we want is anybody got a plastic water bottle? Because that was what we found worked really, really well. I forgot to go and get one. Yeah, that'll do, Karen. Can you, yes, you've emptied it, eh? Can you make sure we haven't got anything else in there? You didn't want it anyway, did you? Not now. Okay. Okay, so you need light to be exposed here. Again, around the umbilicus is good. So if you muscle test her, just in the clear first of all. Okay, now put the 380 on, because some people do weaken to the 380, but it does not mean they've got a cancer, don't worry. Right, so let's see that she's nice and strong. That's good. Okay, now we'll try her with this. This has got bisphosphenol, bisphosphenol A on it. Okay, so it's a plasticizer. So she's nice and strong, okay? So she has no problem with this. So if she has an excess of this in her body, she would go weak to the substance, wouldn't she? But now, let's put the 380 on. So the light now is going through that. You can see a purpley color, violet color, okay? So you say, oh, that was violet, okay? What you can't see is the light coming through there because it's beyond the human spectrum. But you can see what it's reflecting, but there is a light coming through at 380 nanometers. So we're going to put that onto the plastic. So the light is now going through that, like Pop's experiment, and what happens is she goes weak. Okay? That does not mean she's got an overdose of that, an overload of that. Everybody does the same thing. There won't be a person in this room who doesn't weaken to a plastic water bottle. Okay, if it's that crinkly stuff. About, can I go and get the other things? Jane will give you the PAHs, polyaromatic hydrocarbons, and the pregnenolone. Yes, they're in the test files, yeah. About, 4 or 5 years ago, they changed this to bisphosphenol A as the plastic to make the plastic thinner, okay? And before they were quite sturdy, weren't they, the water bottles? But now they put them so they can be recycled and crushed underfoot like I did. And it's got the bisphosphenol A, which is highly carcinogenic. Why did they put it into there and sell it that? Stupid, isn't it? Because particularly if you warm that up, if you leave that out in the sun, then you bring it in and put it in your fridge and things like that, you can taste the sort of the plastic in there. But this, on its own, won't weaken you unless you've got an excess of bisphosphenol A. But when you put this over it, every single person weakens. And to our amazement, there were a number of things that do this. And you can play around with this, because people have said, does aspartame do the same thing? Does Roundup do the same thing? These are all questionable substances. Are they carcinogenic or are they not? Pop discovered this, 50 years ago now. And by simply refracting, does the light go through or does it disperse it? And so what we're going to do is just I'm just going to move the head now. So one of the things that we found is that the benzoapyrene will weaken everybody, and so will all other polyaromatic hydrocarbons, which is what benzopyrene is. It's one of a family of polyaromatic hydrocarbons. So polyaromatic carbons form one of the best markers you can use for a cancer, because every cancer case weakens to polyaromatic hydrocarbons, because they say, don't give me any more of these things. They've already got enough genotoxicity related to this. It does not mean that they've been drinking too much, plastic water. It just is a marker, which means overloads their ability to detoxify that. Okay? So every cancer case that you've had or got will weaken to polyaromatic hydrocarbons. So this is one of the substances we put in a little bag. I think everybody's got those, haven't they? Yeah. Okay. So it's polyaromatic hydrocarbons. You've probably heard of it, PAHs. This is a really, really toxic substance. So if you put PAHs on, she probably won't weaken to this in the clear. But now put the 380 on top of the vial. So that doesn't mean she's got a cancer. What it means is she's doing like everybody does, is they weaken to polyaromatic hydrocarbons. Everybody does this, okay? If you put it under the 380. Now, radium will do this. We have and probably all radioactive materials will do this. In our old detox box, we have radium 1000X. So there's long gone any of the radioactivity, but it's got the frequency of it, and that will. So I guess all radioactive isotopes will potentially are genotoxic. And some interesting ones that we found was the 4-hydroxyestradiol and the 4-hydroxyestrone. These are estrogen derivatives. They're hydroxylated intermediates between the actual real estradiol and estrone and the methoxylated and how they're passed out. So these hydroxylated derivatives are sometimes more carcinogenic than the substance before. So this is why sometimes you don't want to detoxify something if you can't finish the job off. And we also found the 16-hydroxyestrone. Now the 16-hydroxyestrone is the one mainly that affects the boys. This is the one that stimulates the prostate cancers. Whereas the 4-estradiol and the 4-hydroxyestrone is the one with the breast cancer for the ladies. So both estrogens are bad for carcinogenic problems. Okay? But we know that the 4 of the estrone and estradiol are the bad guys. The 2 and the 16 are good, except the 16 of the estrone, which is bad, particularly for the boys. Okay? So you will find in cancer, prostate cancer, always a high level of 16-hydroxyestrone. So they will weaken in the clear. Okay? So if you don't weaken in the clear, you will weaken with that under the 380, which is normal, because what it's saying is it disperses the light and she can pick that up. Now, the one that really flummoxed us is pregnenolone, which is the precursor. It's a hydroxylated derivative of cholesterol, but it's a precursor to progesterone. Progesterone is fine. It's a natural hormone. Pregnenolone is not a natural hormone. It's an intermediate substance which should be metabolized straight on to making progesterone. The pregnenolone weakened under the 380. So that was particularly interesting. Now, you can put anything you want under there. Shall we put a sweet under there? So let's see what you do to this sweet. It does not mean you have a problem. You have no problem with sweets. No, sweets are not carcinogenic. But if you have something which potentially is carcinogenic, then it will show up. Have you got anything else there? Well, let's do a hormone. Let's do pregnenolone just to show them. Yeah. No, the wrappers, she doesn't weaken to the wrapper. No, it's not the bisphenol. We haven't not found a hormone yet? Okay. Right. Okay, so let's just go back here. And you can, this is in your manual, all about polyaromatic hydrocarbons and why they disperse ultraviolet. You can go to this website and it tells you all about it. It's all out there. It's nothing, Pop's work is old hat now, but using applied kinesiology and muscle testing, we can bring it to life. So that's the website to get all the information. And you can look about the transversions, in other words, the mutations that are caused by specific carcinogens. So the exposure to benzopyrene creates a G into T. And G into T indicates a polymorphism which always transfers into a need for a greater amount of pyridoxal 5-phosphate. So G into T polymorphism equates with needing extra pyridoxal 5-phosphate. It's about the only one I can remember, or some of them I can remember. So those are the websites to go to, and they explain all about it, which is interesting.